I will record this again on 16th Saturday, April. You will have test 1 for students who have a valid medical excuse. You need to come with a valid medical excuse printout of that for the test 1. Okay, at 10 a.m. in the morning. Okay. So let's go to the slides and we will continue. Last class, we went through the method to interpolate and obtain the values of EA. Also interpolate and obtain the values of KT and KTS. Okay. So KTS for shear stress and KT for normal stress. Now let's assume we have obtained all these values and we have calculated the normal stress and the shear stress for this particular problem. Okay. So we have two different stresses. In that case, first we need to identify what are the components of stresses we have calculated. It might be required that we also need to know the components of stresses. If you need to know what are the stresses that those are created, in this particular case, we know it is a rotating shaft. So you can draw a shaft and you can fix the directions first, X, Y, and Z axis coming out of the board. So once you fix these directions, then you obviously know that your normal stress is sigma xx, and depending upon the point you choose, either on the top of the shaft, on the surface of the shaft, which one you are choosing, depending on it. Because of torque, you might have tau x y or tau x z or tau x theta in a general direction. Okay. Now let's go back to the values. We have these values. Since we have combined stresses, we have to figure out what is the von Mises stress according to distortion energy theory for a 2D case. And in the 2D case, this is the simple formula. And we can figure out von Mises stress and find the factor of safety. So this is very simple. Now, the factor of safety is more than 1, in which case the life of the specimen is going to be infinite. Okay, you can also draw in the Hague diagram graphically. You may identify the stresses which we have calculated in the Hague diagram on the radial load line. You will also be able to find the intersection points with the Gerber curve or Goodman line, or whichever it is based upon the table. You can also find what is the intersection point with the yield line, and then figure out what are the factor of safety graphically. Okay. So here, what did we find? The yield factor of safety is 3.5, while the fatigue factor of safety is 1.58. Okay, so the yield factor of safety seems to be larger. I think this graph does not correctly show it. The load line, most probably it is in this region, because you see the yield factor of safety is quite low. That means the load line is somewhere here. And sorry, the fatigue factor of safety is low and the yield factor of safety is pretty high. So we are definitely in this region. This means we will get first fatigue failure as we increase the load along the radial load line, and then the yield failure. Okay, so there are different methods shown. I think the first, in the previous problem, let's check it again. Both by Gerber method. Okay. Okay, so this is the result we have. Now let's go to the random fluctuating loads. When you have random fluctuating loads like these, how do we solve problems like these? Okay, the first step here is we need some kind of simplification. So how is the load applied? For example, if you have some shaft, first due to random vibrations, you may have a load like this, and then it suddenly changes and the load appears like this. So how do we replace this? We have to do some simplifications. The simplifications start with replacing this loading with 2 or 3 different loads. First load will be based upon the maximum value here. And we will start with a big cycle. So maximum value, and then goes to the minimum value, and then goes to the maximum value again. So this is one cycle, one big cycle. We will also replace it, or we will have a method to represent the small cycle. Since we have started from here, the small cyclic load could start from this point to this point. So this will be another small cycle. And in similar way, we will also have another cycle here between these 2 points. So these 3 cycles together will represent this random vibration. So we'll see an example problem like that. So we have 3 cycles here. You may have n number of cycles. In general, you can replace random vibrations with n different cycles. Okay, and you can number them as 1, 2, cycle 1, 2, 3, etc. In each cycle, we are going to represent sigma max and sigma min values. It could be combined load as well. So in case it is combined load, von Mises stress. Okay. Now for each cycle, I can figure out what is the number of cycles to failure, and this number of cycles to failure is going to be my capital N here. Cycles to failure. But then you might have applied in, let's say, cycle 1 only small n1 number of cycles. So in cycle 1 small n1, in cycle 2 only n2 number of cycles, etc. So the small n represents actual loading. How many cycles? Loading cycles. Okay. So how many cycles of load you have applied? Okay. If you take the ratio of small n to capital N for a given cycle, and let's say we have 3 different cycles, then you add this ratio. The sum of these values will be equal to some constant, and this is found experimentally. Again, this is a empirical formula, not a theory, but based upon empirical observations or experiments. Okay. Now, what is this constant C? Experimentally, it is found to be between 0.7 to 2.2. But for most of our problems, we are going to consider a value near unity. So this is the average value near unity. Okay, and we are also going to define a damage as D equal to sum of small n over capital. This is called as Palmgren-Minor's rule. This particular relationship is called Palmgren-Minor rule. And this Palm-Grundy-Minor rule assumes some linearity. What kind of linearity? The linearity is in this equation itself. Okay, so let's write this equation. I think this is lecture 26. Section 01. All right. So if I write the summation, sum C, you can see that if I expand it, so it should be small n. Let's say we have 3 different cycles. Let's say I write the damage is equal to this. It doesn't matter in what order I am applying this load. So I could apply this load 1, then 2, then 3, cycle 1, 2, 3, or 2, 1, 3, or 3, 2, 1, or whatever order, whatever combination I apply, my damage is still going to be the same. So there is assumption here. So this implies assumption. And this assumption is linearity. What is linearity again? Just like if you have Hooke's law, you have some linearity, and where we can use the superposition principles to represent the case in the same way. So for example, if I apply a load P for a cantilever beam here, and I have a moment here M, I can split it into 2 different problems, one consisting of load P only, plus the another problem consisting of moment only, and then add up the solutions together and get my final solution. In the same way I'm doing here, I can find the damage for cycle 1, damage for cycle 2, damage for cycle 3, and add them up together. So this is a superposition principle. We have unknowingly applied the superposition principle, and therefore linearity is assumed. For the stresses, maybe if you use the Hooke's law here as well, for the stresses and strains, we have assumed some kind of linearity principle. But is this true? Experimentally, not true. So this is a limitation of the method. So this assumption is not true, and it is found experimentally that if I change the order of loading, then the results are not the same. The damage, in fact, could be different. The results could be quite different. Okay. So this is the limitation of the method. So let's see a simple problem on how to apply this method to calculate what is the number of cycles to failure in this case. So we have with the values here represented, and we are applying these 2 types of load, a random vibration and this combination of the load is repeated again and again. So first this load, second this load, again the first this load and this load. So this is what they have found through instruments. This is the load being applied onto the component. So given a part with SUT value equal to 151 kpsi and SE value is fully realized, SC value is also given. Estimate the number of repetitions of the stress time block, this and this together, how many cycles you can apply before the failure. Okay, let's see the problem, how to do that. First, we need to figure out how to replace this. In this case, we are going to replace it with one big cycle. So let's see. Since the order of the application of the cycles is not important in this particular theory of Baumgarten-Minor rule or assumption. Okay, so first cycle I'm going to consider what is the max and the minimum values. What is the sigma max value here? We have 1, 2, 3, 4, 5 divisions between 50 and 100. That means each division is 10 kpsis. So 60, 70, 80. I'm not going to write the unit, it is kpsi. Okay. Then I go down and I can see here again 10 units below 50, so minus 60. Okay, so let's write down sigma A. Sigma A will be absolute value of max minus min over 280 plus 60. Minus of minus will become plus 60, 140 divided by 2, 70. Sigma mean, add them both, 80 minus 60, 20 by 2, 10. Let's see cycle 2. Okay, so let's first identify here. Yes, we got cycle 1 correctly, 70 and 10. In the cycle 2, we will see here 10 and 50 we are given. So cycle 2 is this guy here. So the max value should be 60. Let's see, what do we have here? The cycle 2, 10 and 50, yes. Sigma min is 40. And let's find sigma A, max minus min, 60 minus 40 is 20, 20 over 2 is 10. And the sigma mean value 100 over 2, 50. So we are right here. Let's go for third cycle. And we have to specifically, let's see here. Since we went to the maximum value, which means here, so this is the values these are the values we should take. Minimum will be minus 40 and the maximum will be minus 20. Okay, so let's say here max minus min will be minus 20 plus 40, so 20 divided by 2, 10 again, and the mean value is going to be, add them both, 40, 60 minus 60 by 2 minus 30. So let's see the last cycle just in case if we have it correctly. Second and 3 here, 10 and minus 30. Do we have that? 10 and minus 30. Okay. All right. So here we also need to figure out what are the material properties, but we are directly given SC value here, SUT value here. Now these are the sigma A and M values. Let's see here. They have used a particular method. They are using the Gerber fatigue criteria. Remember that in the problem you are not asked to use a particular method, but you can choose any method, Gerber or Goodman or whatever you want to choose. So let's choose the Gerber method. Now, if I use the Gerber curve, first I need to figure out what is the factor of safety, fatigue factor of safety. Depending upon the fatigue factor of safety, I need to figure out whether I have infinite life or finite life. Remember, according to the formula here, the damage is defined by this formula, small n over capital N. Okay, so what is it? What is the capital N value? I need to realize that. What is the capital N value? We need to find after we find the NF value. If the fatigue factor of safety is greater than 1, capital N I for that particular cycle is infinite. On the other hand, if my fatigue factor of safety is less than 1, then Ni, I need to figure it out what it is. How do I find Ni in this case? I need to first figure out what is the equivalent completely reverse cyclic load, because we have positive mean stress here, and a negative mean stress over here. So first I need to find for each case, if it is positive mean stress, what is the reversible number of cycles, and then I use my standard formula given here by finding A, B and fatigue fraction. After I figure it out, I will use the formula, this particular formula, to find out what is the number of cycles to failure, capital L. So these are the steps. How do I find the equivalent completely reversed load? And this is we have to use the Gerber criteria. I invert, we use the same method as before. Okay, what do I do? I will have to draw my Hague diagram. If you recall, sigma mean, sigma A, and you will have the Gerber curve. And let's suppose our point is here. I will draw my Gerber curve. It passes through the red point, extend it, and it intersects on the y-axis some other point, and that I will call it as the sigma reversible. How do I find this point? I write the Gerber equation. Let's see. If you go to the book, we can quickly find the Gerber equation. This is the Gerber equation we should use. So without the factor of safety or with factor of safety, you can use it. Sigma A by sigma reversible. We are going to replace SE by sigma reversible and then plus sigma M over SUT square must be equal to 1. So we can assume for simplicity n is equal to 1 and get rid of it. And then we will be able to write an equation for sigma reversible. Okay, so in the denominator I will have with the n value this is the value we will have, and in the numerator sigma a. So this is the same formula that is written over here for positive values of sigma. Remember, the Gerber curve is valid in the positive direction. What about in the negative direction of mean stress values? In the negative direction, we know that we just simply use the SE value here as the limit. So if it is sigma mean value is negative, then you will just use the equivalent value is SE. Okay, so sigma reversible value will be SE value, and based upon that, based upon the SE value, we can decide what is the factor of safety and then figure out whether it is infinite life or failure has occurred. Okay, so let's go cycle by cycle. Let's go to the very first cycle. We know sigma A and sigma M values, 70 and 10 here. Take the ratio, we will get the R value. We can, to find the fatigue factor of safety from the tables, you can use directly the formula, or I find the intersection points graphically. Once I have the intersection point, I can figure out whether what is the fatigue factor of safety. Once I find what is the fatigue factor of safety, I will know that. So let's take this for granted. SA value is 67.2 for cycle 1. Cycle 1, 67.2 kpsi. Remember your graphical method, you will have the numerator SA times 1 plus 1 over R square over sigma A times same 1 plus 1 over R square. These terms will get cancelled and you will simply have SA over sigma A. What's the sigma A value? For cycle 1, we know it is 70. So obviously, what we find here is this guy is less than 1, which means we have finite life. In this particular case, we have finite life, which means the next step is figure out what is the completely reversible load, and we use the formula given here. Sigma mean value is positive 10 kpsi, so we use this formula. Okay, what is the formula? Will be sigma A over 1 minus 10 over SUT value. Let's see here again, we need the SUT value 151, and figure out this sigma reversible value. So when you use that, you get 70.3 kpsi. Now here we have already found out what is small f fatigue fraction, and then we figured out what is A and B, and finally reduce the formula here to find the capital N value, number of cycles to failure. We can use this formula directly, and they have found 619,000 cycles as the answer for cycle 1. If only cycle 1 is applied, then this is the number of cycles to failure. Okay, so let's keep this here. Let's try for cycle 2. In the same way, 10 over 50, we get 24.2. Sigma A value is 10. And what do we get? So fatigue factor of safety in cycle 2 SA over sigma A, and if you do that, SA is 24.2. The sigma A value, again, if you don't recall from here, sigma A value is equal to 10 for cycle 2. Greater than 1. What is the number of cycles to failure? In this case, N2 is infinite number of cycles, greater than 1, right? So in the same way, let's see for cycle 3. Cycle 3, we have the mean stress negative, in which case we have to use the SE value. If you use the SE value, we can see for cycle 3, SA value is equal to SE is equal to the value, that is the value, SE value 67.5. Kp is I. Okay, so again we can find the fatigue factor of safety as SA over sigma A, and let's go back in the cycle. Sigma A is 10. Is greater than 1 implies infinite cycles. Again, N3 is also infinite. So now we find the damage by using the formula. Okay, how many number of cycles do we apply? Let's go to the estimate the number of repetition of stress time block. This is what we use. If you take one cycle here, in here, this is a complete stress time block. How many stress time blocks can we apply? Let's assume we apply n. I'm going to use small n number of cycles, like stress time block here. So with this means if I apply this entire block n times and then failure occurs, this means I apply the big cycle small n times. I apply these two small cycles, cycle 2 and 3, also small n times. Okay, so from here I can write capital N over small n1 plus small n over capital N1 and small n over n2, small n over n3. So this is the damage. We have already figured out what is n1, n2, n3. Take n commonly out, right? That's 1 over n1 is, if you recall from the calculation, 619,000 cycles. N2 is infinity, N3 is infinity. Now, according to the Palmgren-Minor rule, this damage must be equal to 1 unless you are given some other value for the C value on the right hand side. We assume it is equal to 1 and then calculate n. What is 1 over infinity? It is 0. So this term goes off to 0. This term also goes off to 0. That gives me n is equal to 619,000 cycles. So this is the number of cycles to failure for randomly applied load according to Palmgren-Minor rule. Is it clear? Is the method clear? Okay. Okay, so as I told, we have assumed linearity for the Minor's rule, and these assumptions are not valid for the case of most of the materials. And there is also another disadvantage in that the Palmgren Minor rule predicts a change in value of the, let's see here, what is the value here? You can see here in the experiments conducted, usually in the experiments conducted, we will have your the SN diagram. Usually we will have the SUT value here, right at the intercept given here. If you go back to the SN diagram, let's see here. Let us find here. So this is the SE value. This is the Hague diagram. We need to see the SN diagram. Let's see where is the SN diagram given. Just 1 second, hold on a second until I get my SN diagram from the experiments. Looks like it is behind here. Okay. So in the SN diagram, you can clearly see the Y intercept over here at 10 power 1 cycles is exactly equal to SUT, or in experiments it is really found to be 0.9 times SUT. However, in Palmgren Minor rule, this is the SN diagram again, you can see according to the Palmgren Minor rule, it predicts a value of the intercept here on the SN diagram below the usual value of SUT. But in experiments, it's found that such a prediction is very wrong. It is wrong. It is not right. So again, it wrongly predicts Minor's rule, wrongly predicts the SUT value, static strength SUT here. Why? Because as I extend and go to 10 power 0 cycles, so this is 10 power 3 cycles. Let's go to 10 power 0 cycles. It must intersect at SUT exactly. Okay, however, it will predict a value lesser than SUT. So this is not true. SUT value will not be damaged. Experimentally, it will not be damaged. Okay, and the second one is the linearity assumption. So that is also not true. These are the two disadvantages for this particular Minor's rule. There is a slightly different method which is called Manson's method, which overcomes this and predicts the SUT value correctly. Okay, we will not go through the Manson's method as well. We are in the last part. In some problems, especially if you have problems where you have surfaces which slide against each other or roll against each other. For example, two gears. If you take the gear teeth, they will slide and roll against each other. And because of that, we will have what is called as contact stresses. In the previous chapter, we went through some formulas from some formulas for two cylinders in contact or two spheres in contact, and those formulas were called as Hertz stresses, contact stresses. We are going to use the same Hertz stresses to figure out, in the case of cyclic loading, what are the amplitude of contact stresses for simple cases like two cylinders or two spheres in contact. What about other cases where we do not have cylindrical surfaces in contact or spherical surfaces in contact? There, for contact problems, we have to use FEA, finite element analysis, and figure out what are the local stresses and then try to solve the problem. Okay, so again, contact problems are not very simple. Even the two surfaces, dry contact surfaces, even solving that problem is pretty complicated. But in general, these contact surfaces are usually lubricated. Then there is another complication where as two surfaces rub against each other, temperature increases. If temperature increases, expansion will occur. If expansion occurs, stresses increase. Stresses increase, again temperature increase. There is a cyclic effect. So all these things complicate the calculation of stresses at the contact surface a lot. On top of it, you may also have wear and tear, wear of the material over a period of time, diffusion of foreign elements, and so many other things that take place in contact situations. So design of components which have contact surfaces is not that very simple. It is a highly complicated situation. Okay, but for initial purpose, usually we avoid, for design calculations, avoid effects of lubrication. Maybe we bring in some temperature effects, and we also avoid maybe wear and tear. So these two parts are pretty complicated. Wear, tear, maybe some diffusion, all these things we will simplify. It is possible to include on a simple model temperature and stresses and couple them both and make the calculations. So let us see some analytical formulas from previous class. We have seen two cylinders in contact. These are the formulas we have, and finally the contact stress is defined this way. Okay, and let's see here. We define Pmax as the surface endurance strength, which is given by this formula over here. All the constants are evaluated here. E1, E2 are the Young's modulus for two cylinders, Poisson's ratio for two cylinders, and the corresponding radius for two cylinders, the force applied between them. And based on this, we calculate what is Pmax based upon after we define the Pmax, we define what is called as the surface endurance strength, which is represented as SC. C stands for contact, and this is the endurance strength. Okay. Finally, after combining certain equations, we get these equations and we get a relationship to figure out whether the to figure out what are the stresses acting on the component. Again, you can see some experimental values for K1 and Kg, some of the properties, and again based upon experiments, the contact strength or the fatigue strength due to contact is related to the number of cycles to failure by this relationship. And then we can figure out what is the number of cycles to failure. Again, for your exam, I'm not going to give you these problems. This is just for your knowledge. Okay. So how do I figure out in case I want to find out what is the contact fatigue strength for materials, just like endurance strength. So at 10 per 8 cycles, we can figure out what is the endurance strength based upon these empirical formula for steel. And we can see here, based upon the hardness value, we can get it. Again, there are two different standards given here at 10 per 8 cycles, and according to AGMA for gears in particular at 10 power 7 cycles, you are given what is the surface fatigue strength. Again, there are formulas given for gears as well. Okay, so I'm going to stop right here and completely skip the stochastic analysis. If you are interested, you can go through it. In the old version of the book, you have stochastic analysis. Why do we need this? Because whenever there is some kind of uncertainty with respect to the material properties, then we will have to use stochastic analysis to solve the problems. And you can see some kind of a distribution given here. Maybe this is not exactly normal distribution. This is unsymmetric. So you may have different distributions which are involved based upon probability calculations. You will calculate what is the endurance strength and then proceed with the problem. Okay. So we are done with this chapter, and we need to go to a new chapter, which will be the first chapter on applications. So we will start with shafts, and we have 3 more chapters to be covered. What are the 3 more chapters? Shafts, fasteners, and springs. I think we will go in a certain order. So with respect to applications, design of shafts, springs, and fasteners. Okay. So let's take a 10-minute break and we will continue after 10 minutes. We'll meet back at 9:20 a.m. Okay. See you guys at 9:20. Can you guys hear me?
Yes, doctor. Okay.
9:20. Okay. See you guys. Are you guys able to hear me? Are you guys there?
Yes, Dr. We can hear you.
Yeah, okay. All right, so we'll start with a new chapter. This is going to be on shafts, design of shafts and accessories like keys. Okay, so we will see some examples on how on shaft is assembled and what are the different components used to assemble these shafts and gears and pulleys, etc. We will see the general shaft layout, and then from there we will see what kind of loads are applied onto the shaft. And then we are going to divide the design of shafts into two or three different cases, or two or three different design formulas based upon design formulas. Okay, so the shaft design will consist of a static load case. We will have a dynamic load case, fatigue stresses, as we have seen. So static failure theory will be applied, and then fatigue failure theory will also be applied to calculate the dimensions of the shaft. Now, often this type of calculations will be repeated calculations, and it is quite a long procedure. The actual design calculations are pretty long calculations here. We have to repeatedly do the calculations again and again. In addition to that, since the shaft is rotating, we need to consider resonance frequency. This is very, very important phenomena, and we have to ensure that we never run the shaft corresponding to the resonance frequency. If we do that, it will lead to failure of the shaft. Okay, so we will talk about resonance frequency as well, and something about material selection process. That will be also there. Material selection, what kind of materials are used, and briefly about manufacturing processes. Okay, so this is going to be the overall outline of the chapter for the shaft design. In addition, we will also go through some of the miscellaneous shaft components that that will come along with the shaft. For example, keys for shaft, etc. And then design of keys. Whenever you put a keyway inside the shaft, leads to stress concentration effects, and we should know what type of shaft components we should select. In addition, shafts are usually we provide an interference fit between the shaft and bearings. So in that case, we need to have standards corresponding to the tolerances and fits for shaft. So we will study something about limits and fits as well. Okay, so we went through this already. So again, we'll start with material selection, geometrical layout. We will differentiate between stress and strength properties. Also, I forgot to mention, we also need to consider deflection and rigidity. We cannot allow, in the case of the shaft, too much deflection. So our selection of the material should ensure that the shaft has sufficient stiffness. So this is very important. Stiffness not only due to the bending moment loads, but also torsional deflection should be considered. All these will be considered. Okay, so when we talk about stiffness of the shaft, it could be torsional stiffness or bending stiffness, and it is usually controlled by geometric parameters. Okay, deflection usually is controlled by geometric parameter, also to a certain extent by the material property E. So we cannot say it is completely not controlled by material. It is controlled by E value. Okay. However, generally we choose steel Steel will always have a particular E value. No amount of alloying is going to change the E value, okay, for steel in particular. So this is why this the value of E becomes a non-issue with respect to the deflection here. So we usually control deflection in steel shafts by controlling the geometry. Again, stress is also controlled by geometry and not material. Again, recall that your stress has the formula force over area. So it is only geometry that controls it. If you have bending moment load, then you have the formula M over I, or maybe section modulus Z. Again, section modulus depends upon the geometry. Or if it is torsion, then shear stress also we can consider T over J times C. J and C are geometric parameters, and nothing about the material comes in. Strength is, of course, a function of material we choose. Strength is a function of material. Shafts are usually made out of low carbon steel, cold drawn or hot rolled steel, and usually the materials which are selected are these materials according to ANSI standards, 1020 or 1050 steels. You can also consider it as AISI. Okay. Fatigue properties usually benefit, don't usually benefit from much alloying. So how much ever alloying you do, your SE value does not change. Your E value does not change. Okay. However, with alloying, maybe the yield strength changes. Okay. The only property which can change is the yield strength. So SE value, E value, SUT value, all these values will not change with alloy. Okay, so how do we improve SE values? One method is you can do some surface hardening. If you make your surface very hard, it is scratch proof. If it is scratch proof, then the fatigue properties automatically improve. Different methods by which we can do surface hardening is by carburizing, nitriding, maybe you provide some kind of a surface coating. All these things will improve the properties, the fatigue properties of the shaft. Okay, so mostly we use steel. We have seen the material. Let's go to the manufacturing very briefly. If the diameter of the shaft is less than 3 inches, then we use the cold drawn steel for the application. For larger sizes, we use hot rolled steel. The larger the size, forming them into different shapes will be difficult without applying some heat and deforming the material. So after the forming process is over, we also need to do some kind of machining to ensure that the dimensions are close to our quality levels. If you use lesser, let us say for low production quantities, number of shafts you produce is less, then usually we go by machining processes. For high production quantities, we go by forming and casting. So what is the typical layout of a shaft? So you can see here. So shaft usually involves a lot of steps here. You can see varying diameters, and gears are mounted in certain locations. Bearings support in certain locations. You can see here this particular step is required to position the bearing here. You can see a roller bearing and maybe a ball bearing over here. Okay, so in order to position the bearings properly, we can see several steps provided for the shaft. So what is this issues to consider for the shaft layout, axial layout of components, supporting axial loads, providing torque transmission, assembly and disassembly. So depending upon whether your shaft is horizontal or vertical, if you have the vertical position of the shaft, then definitely you will have an axial load. If there is axial load, then it leads to complications. In the slight complications in the calculations. Otherwise, you will usually have a radial load. For example, this gear will lead to loads in the transverse direction, depending upon where the gear is in contact with another gear. And in addition to that, this radial load will cause some bending moment load. In addition to that, you are providing a torque onto the gears here. Because of the torque, you will also have torsional load. So typical arrangement for horizontal shafts, you can see two gears loaded, and this represents the bearing locations. In this particular case, you can see two ball bearings are used in the stepped shaft to position them properly. The bearings enable rotation of the shaft without much friction, and you have gears and pulleys here. Again, gears and pulleys are also located with the steps provided in the shaft. So providing steps in the shaft is very much a necessary element of the shaft. Whenever you provide steps, what will happen? Stress concentration effects. And you need to carefully design your shaft for that. Okay, so this is another example giving you a clear picture of how the shaft is supported. You can see here, step shaft here, vertical shaft, supported by taper roller bearings. These tapered roller bearings usually carry the radial load and axial load. So let's see an example here. Okay, so this is an example of a tapered roller bearing. You have rolling elements. This is the outer race. There is the inner race. They are disassembled here, but usually you can assemble it back. And the outer race is usually fixed to a hub. Inner race, through the inner race, you have your shafts passing through it. And there is an interference between the inner race surface and the shaft surface. What is an interference fit? There is a tight fit between the bearing inner surface and the shaft outer surface. So which means the diameter of the outer surface of the shaft will be slightly greater than the diameter of the inner surface of the bearings. So you have to use a hydraulic press to force these bearings inside the shaft. So after you do these fits, the shaft is supported and it can carry axial as well as the radial loads. You can also see a hub here. On this hub, you have a gear which is mounted. These are bevel gears. Bevel gears are usually used to transmit rotary motion between two perpendicular shafts. So again, there are various types of gears. So this is an example of a bevel gear, and you can see clearly you can transmit rotary motion at different angles depending upon the angle of the gears here. So through the hub, these bevel gears are connected, and you can see between the horizontal shaft and the vertical shaft there is connection between two bevel gears for transmission of the loads. Here we have ball bearings instead of roller bearings. Okay, so let's see here again. How is the hub connected to the shaft? You can see the small portion here. This is the keyway. Using keys and keyways, we can connect the hub to the shaft through the key, rotary motion from the shaft to the hub is transmitted. Okay, so again, if you want to see keys and keyways on shafts, if you just look for it, you will get it. On the images here, you can see there is the key seat, this is the hub, and you can insert using the keys and key seat. Both of them will be, there is a key seat here, there is a key seat here, both of them will be connected, and keys are usually used for transmitting only the rotary motion. It will not carry any axial load. It cannot carry axial loads. There are various methods we can connect different parts to the shaft. One of the ways is keys, and then we have splines, set screws, pins. You can also use press fits or shrink fits or interference fits, which we already talked about. And there are also tapered fits. So among these, keys are the most effective way to transmit rotary motion. Okay, the shaft design for stresses. So first we are going to consider stresses for design of the shafts, and then we will go for frequency. So how do we design the shaft? First, the procedure is same. First, we need to identify the critical locations on the shaft. Wherever we have stress concentration effects on the outer surface where the stresses are supposed to be maximum. What kind of stresses are maximum on the outer surface? If you recall, it will be the bending stress is maximum on the outer surface. Torsional stresses due to torque, they are maximum on the outer surface. And definitely we also have, in addition to that, any stress concentration effects which may occur on the surface. So at the outer surface, bending moment, torque is constant, is maximum, and stress concentration effects also exist. Okay, so what are the equations? Now we may have a static load or a dynamic load here. Okay, so we need to consider both the cases, and in the fatigue equations we look for both static yielding and also fatigue failure case. So in this case we need to find, as usual, the amplitude of stress and the mean stress values. We have bending moment load and torsional load. These are the usual loads. In addition to that, if you have an axial load, we need to also consider that. So this means we need to consider the von Mises stress. Since we have combined load, we need to consider the von Mises stress and calculate von Mises stress for a combination of the loads. We will use the fatigue stress concentration factors both for normal stress and the shear stresses. Let's see here. We can substitute. Usually shafts have circular cross section. Therefore, we can substitute for I as pi over 64 d power 4, and C value is equal to d over 2, and the J value is equal to 2 times I. Okay, otherwise pi over 32 d power 4. If you substitute all these quantities, it reduces to this formula with the amplitude of moment, mean value of moment, and corresponding torque values. Now we can combine both these stresses. So we need to find the von Mises amplitude and mean stresses. A 2D formula, we already know that. You can utilize this formula. Suppose if you have an axial load in the shaft, in that case, we will have to use the von Mises stress we have seen earlier in the previous chapter. Again, what is the combined stress we have seen? Let's try to recall that. I think it is in the, no, it should be here in the fatigue case. Let's see here. I think no. Hold on 1 second until I bring that particular formula up for combined stresses, and then we can move on. Okay, so for the combined load, this is the formula we have seen before. Okay, so what is the stress? We are using the same kind of stress here. Okay, sigma a square plus 3 times tau a square. We used only the bending stress. In case you have an axial stress, you will also include this particular factor over here. For mean stress, you will have 0.85. In the other case, sorry, for the amplitude, you will have 0.85, and the mean stress, you will not have any factor. You can substitute all the values here and write the stresses in the explicit form here, sigma A and sigma M. Now, once we have this, since the shaft is made out of a ductile material, we can use one of the 4 theories. What are the theories? Again, Goodman, ASME elliptic, Gerber or Soderberg theory. In the theory, you can substitute these values and try to solve it. Okay. Now in this chapter, the values are already substituted and you are given a formula in explicit form. In your exams, these explicit forms will be provided to you. To find the factor of safety, this is the formula. After we substitute for sigma A prime and M prime from these 2 equations, they simplify to this form. This is the formula for factor of safety, and there is a formula also for finding the diameter D by inverting this formula in terms of factor of safety and other values. So this is for Goodman equation. Similarly, let's see the other equations. We have Gerber equation formula, ASME elliptic, and Soderberg formulas. Okay. Okay, so how do we use the 4 different cases? In each of the case, for example, if you consider Goodman criteria, you need to consider the yield criteria as well. In these cases, you not only need to check for failure criteria based upon the Goodman criteria, you also need to consider yield failure criteria. We will also see the formula corresponding to that later. So in the case of Goodman, Gerber, and ASME elliptic, yield criteria must be also checked. So let's see if we are given the yield criteria. Okay, so here, so this is the yield criteria in the explicit form, and we will consider these as well. The other, except Soderberg theory, for all the other theories, we will also need to check the yield criteria. Okay, so we also went through this. Let's go back and see how to apply the formulas. If you take your shaft in particular, in general, you will have a completely reverse bending moment load. Reverse bending moment load and a steady torque applied onto the shaft. In general, this is the case. So what does this mean? If I apply a steady torque, that means my TA is equal to 0. If I apply a completely reversed bending moment load, that means my mean value of bending moment is always 0. So m is 0, Ta is 0. That means in each of the formula which I have considered, this term will go off because mm is 0 and Ta will go off. These two terms will disappear. So I can remove these terms and simplify the formula further. So this is the general case for shafts. Why is it a completely reverse bending moment load for shaft? It's pretty obvious when we draw the diagram. Usually we will have a gear, assume this is a gear, and then we have some kind of bearing support over here, simply supported, and the gear causes some weight at this point, which is always acting downward. So this gives us a bending moment. You consider any point A at a particular time, where is the neutral axis? Right in the centroid here. So at one moment you have the maximum compressive load here. The same point comes down here after some time and it leads to the tensile load over here. But since we have a circular cross section here, whether the point on the top or the bottom, we have the same magnitude of stress. So if you consider this as minimum, here it will become maximum tensile. Okay, the magnitude of stresses on the top and bottom are going to be equal, which means it is a completely reverse loading, bending moment load. Usually the shaft is connected to a motor, right, and which applies some kind of a torque onto the shaft, and the motor usually rotates at a constant speed here, RPM, and it will provide usually a constant torque also. So which means it is a steady torque. Since we have a constant RPM, we can clearly see my bending moment will have a fixed frequency depending upon the RPM, and this fixed frequency load will be applied to the shaft, while your torque is just a constant value. Okay. So this is clear, and we can solve an example problem. We will solve a problem next week. For today, this is enough. Any doubt up till this point? If you don't have any doubt, I'm going to stop here and we will meet again on Monday. Again, I repeat, on Saturday 16:10 a.m. you have a test for students who have missed the test 1 due to valid medical reasons. If you have to bring your medical certificate for the test 1 on Saturday 10 a.m. Okay, so see you guys, and I will meet you on next class.